We were learning about Lewis structures, and we talked about ionic bonds, and now we're going to talk about covalent bonds with Lewis structures. So a Lewis structure for a molecular compound is going to show neighboring atoms sharing electrons to get octets, or for hydrogen, a duet. So here we're going to use Lewis structures to show bonding in water and chlorine molecules. We're going to identify the bonding pairs and the lone pairs. So let's do water first. So the way we looked at the ionic compounds is first we drew the Lewis symbols for the atoms, and then we looked at how they could get octets. So how many valence electrons does hydrogen have? 1, right? And how many does oxygen have? 6, because it's in group 6A. Oops, there, 6, a little crooked. So oxygen has 6, oxygen wants 8. Hydrogen has 1, hydrogen wants 2. But these are both nonmetals, and so they're not going to form an ionic compound. They're going to share electrons instead. So oxygen would like hydrogen to give her that electron, but hydrogen's not going to do it. So they're going to share it instead. So we'll say, okay, well, I'll share one with you and you share one with me. And when you share something with another person, then it kind of belongs to both of you, right? So now when hydrogen looks at its electrons, it says, oh, I have 2. I'm good. I'm like helium now. Love and life. And the same thing's going to happen with this other hydrogen, going to share an electron with oxygen, and oxygen will share an electron back. And so this hydrogen is also happy with this 2 duet of electrons here. The oxygen now counts these electrons, 2, 4, and all the shared electrons, 6 and 8, and so the oxygen feels like it also has 8 electrons. So sharing is a good thing, right? So they can't agree on who's going to lose electrons to make somebody happy for an ionic compound. They're going to share. And this is a covalent bond because they are sharing valence electrons. So we would call the 2 electrons here a bonding pair. So maybe we'll highlight the bonding pairs in yellow. These are bonding pairs. And then there are lone pairs, and lone pairs are not shared. And so the lone pairs would be these pairs of electrons on oxygen. So the water molecule has two bonding pairs and 2 lone pairs. Any questions? Let's do the same thing for a chlorine molecule. So chlorine is a diatomic element, forms molecules consisting of 2 chlorine atoms. How many valence electrons does a chlorine atom have? 7. So I'm going to put 1 there and 6 around here. I'm going to do this one like this because I have a plan. So there's 2 chlorine atoms with 7 electrons each, right? Both of them want 8. This chlorine can't convince the other chlorine to give up an electron. And this one can't convince the other one to give up an electron. Then you'd have an ionic compound, they'd be attracted to each other, and everybody have 8 and be happy. But it's not going to happen. So again, they're going to share. So each chlorine shares 1 electron with the other chlorine. That forms a bond between them, right? Like if you and your significant other maybe were sharing a dog, right? Then that kind of pulls you together. You kind of have to work together with the dog, right? And then things get really can get ugly if you break up and who gets the dog, right? It kind of pulls you together. So this is a shared pair of electrons, but the shared electrons get counted by both atoms. So this atom counts 2, 4, 6, 8, and this atom counts 2, 4, 6, 8. So the bonding electrons got counted twice. So let's identify the bonding electrons, the bonding pair, that's this guy right here, pair of electrons, and the lone pairs, and the lone pairs are the ones that are not being shared. So this chlorine has 3 lone pairs, and this chlorine has 3 lone pairs. Any questions? Now, when we just write out the Lewis structure, we would just put a single line there to represent a single bond, a pair of electrons. But I like to do it this way to start out because we can still kind of see, oh, that was an electron from hydrogen, an electron from oxygen, and we drew a line that connected them, and that's them sharing the electrons. So that's a single bond where you have a single pair of electrons being shared. But you can share more than a single pair. So let's look at the double bond that forms in O2. So O2, 2 oxygen atoms. How many valence electrons do they each have? 6. So how many valence electrons an atom has? That's something that you need to get really good at because we end up asking that question a lot. It's just a group number, right? Oxygen, group 6A, 6 valence electrons. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So we're going to see if we can get these two guys together and make them both happy. Well, let's try sharing an electron. They each share 1 electron with the other atom. Now each oxygen can count the shared electrons. So this oxygen has 2, 4, 6, 7, and the other one also has 7. So that's better than 6, but we're not going to just settle for good enough. We're going to go all the way for 8. So what if we do some more sharing? Let's share another pair of electrons. And now we have 4 electrons that are shared, 2 pairs, 2, 4, 6, 8, 2, 4, 6, 8. Both electrons have octets. And we would normally draw that with a double line for a double bond. And then we'd put the lone pairs on there. It doesn't matter exactly where around the oxygen you put the lone pairs. Any questions? Yes?
The goal is to get to 8 every time.
8. 8's the magic number. Yep. Hydrogen is just trying to get to 2. Basically, you know, all the noble gases, those are like the cool kids in high school, the in crowd, right? Everybody wants to look like them. And so if you get 8 electrons around you, then you are dressed like the cool kids, right? So hydrogen's too small to try to have 8 electrons, but helium is in the in group with 2 electrons. So hydrogen's just trying to look like helium and get 2 electrons, the closest noble gas. Okay, let's look at nitrogen. So nitrogen has a triple bond. So nitrogen has 5 valence electrons. It's in group 5A. And if they each share 1 electron, now we've got 6 electrons for each. If we share another electron from each, now we've got 7. If they each share 3 electrons, now we have 8. So that's a triple bond because 3 pairs of electrons are being shared. And we would show that as a triple line for a triple bond. And then each of these nitrogens has a lone pair. So when we count electrons for this nitrogen, there's 2 here, and each line represents 2. So 2, 4, 6, 8. And for this nitrogen, 2, 4, 6, 8. They have octets. When atoms have octets, they become more stable. And so here we see that by 2 nitrogen atoms forming a diatomic molecule, or 2 oxygen atoms, or on the previous page, chlorine atoms, they become more stable. And this is a big reason why these are diatomic elements, because they are more stable when they have a friend to share electrons with. Questions? So we can use the Lewis model to predict whether a given molecule will be stable or unstable. So let's look at water, H2O and H3O, and see what we find. So we already did the Lewis structure for water. So I'm going to just sketch that one out here. So there's water. And then if we're doing H3O, we have 1 hydrogen, and we have an oxygen, and we have another hydrogen, and another hydrogen. The 3 hydrogens, right? You might say, well, hey, this is looking pretty good, right? This hydrogen shares with oxygen. We make a bond. And this one shares with oxygen. Oh, wait a minute. I got the wrong number of electrons on oxygen. There we go. It had 6. This hydrogen's trying to share with oxygen, but oxygen already has a pair, and if it shares one of these, now it's going to have 9. If 8 is good, is 9 better? No, 9 is terrible. That's too much. We want 8, exactly 8. So if this were to form a bond, then our oxygen has 9 electrons, which is not good. And so we would predict that this is not stable. Could it form? Possibly, but it wouldn't stick around. Okay, so we have a question. Well, what if we have a question like this? What would we do? Would we say it's not stable? You won't actually be given any questions like this. This is just to illustrate that we can use the Lewis model to predict that this molecule doesn't really exist. So that's not stable. So then we're going to look at H3O+. Well, what's the difference between H3O and H3O+? We need to lose an electron, right? So if I take this guy and take off an electron, oh, now things are looking much better. Right? Now it's got a positive charge, but that will be stable. The brackets are to keep the charge out of the dots so they don't get all mixed up in each other. We wouldn't want a negative sign to look like a stray single bond or something.
That's how we would properly write it.
This would be the proper way to write the Lewis structure for H3O+, which happens to be called the hydronium ion, and that is stable. Let's look at another one, H2O2. So the hydrogens have 1 electron. Each of the oxygens has 6. And so if the hydrogens share with an oxygen and the oxygens share with each other, then we can get octets for the oxygens and duets for the hydrogens. So this is hydrogen peroxide. It's not super stable, but it is stable. Any questions? Pardon me? That's a good question. The more bonds it has, the more stable. Not actually. Lewis model, you're going to be able to predict that yes, this molecule would exist. It's stable enough to exist. Relative stability, you probably wouldn't be able to get anything out of the Lewis model. Yeah. So we checked our ideas about the ionic bonds with reality. So let's check these covalent bonds. So the covalent bonds are highly directional. It's a pair of electrons shared between two particular atoms. It's an attraction only in that one direction for each of them, right? So that's very different than an ionic bond where there's attraction all over the place. Yeah, you got the trains. I'm really disappointed somebody erased all of ours from last week. Yeah, we're going to have to move them over further. So in covalent compounds, yes, we hear you.
Just imagine when we go on the other side of the wall.
Yeah, that would be louder. Okay, so unlike ionic compounds, covalent compounds have discrete molecules. They have these individual molecules. Well, what holds the molecules together? Not covalent bonds, but there are some intermolecular forces that we will look at later, but those are much weaker than bonds. And so because those weak forces between the molecules are all that's holding them together, covalent compounds tend to have lower melting points than ionic compounds. So this is an illustration of pentane. And you can make a liquid out of pentane, but it has these very weak intermolecular forces that hold them together, and at very low temperatures, they have enough energy to break away and get into the gas state. So we'll talk more about that later.